All right, this is PreCalculus B Portfolio for Unit 6, the Storm Tracker Portfolio. We're going to be working with something called parametric equations. That is where the x and the y values of a graph are dependent on a third variable, in this case time. And we're going to use this concept to track an actual hurricane, a storm. I'm going to bring up the worksheet here. And so you're to go to this website, Historical Hurricane Tracks. Let's go to that. Okay, and we can type the name of a hurricane, a location. By the way, hurricanes are really named by location. In the Caribbean and the Atlantic, they're called hurricanes. In the Pacific, they're called typhoons. If they don't make it to hurricane status, they're called tropical storms. But they're typically named, and here in the United States, we hear mostly about the ones that start in the Atlantic and end up in the Caribbean or on the Atlantic seaboard. The one I'm going to search for is probably the most famous of recent memory, Katrina, which struck in 2005. It's hard to imagine that that was 17 years ago now. And you can see the path that the hurricane followed. And it takes a little while for it to load here. Here we go. Once we click on the Katrina and get the details, we can see the strength of the hurricane by the size of the dots, and we can see the path the hurricane followed. What we're going to do is we're going to record the latitude and longitude numbers. Now, if you don't have that information here. It tells you all about wind speed and all kinds of category and pressure and date and so forth. It tells you the actual location. If you hover over the mouse, you can look on the bottom right of the screen, right down here. It's 0, 0 because I'm off the screen. But as I move the mouse around, it gives the latitude and longitude. Latitude is the first number. Now note that latitude is how far north or south, how far in degrees, how far north or south you are above or below the equator. And so that actually, if we're thinking rectangular coordinates, needs to be our y value. And the negative 68 there, that's our x value. And you're going to find all coordinates, GPS coordinates in the Western Hemisphere are negative because they start from Greenwich, England, and go to the west. To the west of Greenwich, England, the Western Hemisphere is negative. All right, so basically what I'm going to do is I'm just going to zoom in so I can get a little more precision, because it depends on where your mouse is. So you hover over a spot and you read, I read 23.0612 and negative 75.0070. Remember to reverse those. Negative 75.0070 is the x value. Okay, and 23.0612 is the y value. Okay, now I've already gone through and I collected every other dot. If you collect every dot, that's quite a few points. I collected every other dot, and I pasted them in Microsoft Excel right here. So I've got 16 data points, all with a timestamp. So I'm just calling them for the sake of simplicity. They give Zulu time, which is military time, but I'm not really interested in tracking the time that accurately. So I just marked the time 0, 1, 2, 3, 4, 5, 6, all the way through 16. And I've got my corresponding longitude values, which are my x values, and my latitude values, which are my y values. Note that the latitudes are all positive, and that's because we're in the northern hemisphere, and even the Gulf is in the northern hemisphere entirely. And so this is the degrees of latitude. All right, so the reason I've entered them here in this spreadsheet is I'm going to actually do the analysis in Desmos, but rather than having to retype and retype repeatedly because I'm going to have to create 3 separate tables. I thought I'd put them in Excel, and you can copy and paste cell blocks from Excel into Desmos. So let me get Desmos up. Okay. And normally you click plus and table and you can type in values, but what I'm going to do here is just copy and paste. So I'm going to copy and paste the X and the Y values, just the X and the Y values. So copy with Control C and paste with Control V. You can right click as well. Okay. Now it's automatically jumped to the graph here, zoomed in on the graph. Oftentimes in a table you'll see a magnifying glass to zoom in. Let's see if I can get that to come up. No. All right. And so you can see the storm that we've tracked. And lo and behold, it seems to fairly accurately represent the path the storm followed here. Okay. So we got that shape right here. It's a little bit distorted. Remember that there aren't really truly parallel lines in the sense of the word we think of lines that never intersect on the map, because it's the surface of a sphere. It's not a flat surface. So there's going to be some distortion. Yeah, and I'll leave it at that. Okay. So our trick now is to create a parametric equation based on time that tracks this storm, that follows this storm. We can use it for interpolation, that is determining points between, but more importantly, and this is how it's really used, it's where we get the computer models that extrapolate. That is, we want to know where the storm is headed, right? And that's always the great question. Where's the storm going to make landfall? Where do we need to prepare and make sure the resources are available? The sandbags and relief equipment and everything else. All right, so what I'm going to do now, and we'll come back to this, is I'm going to copy and paste into Desmos a table of just the t values and the x values. T values and the x values. So copy. And I'm going to click in the next cell and right click and paste, or Control V to paste. I don't see a right click and paste, so Control V to paste then. Okay, and notice the headings now, and it's jumped to that graph here again. There's the magnifying glass now on this, so I can zoom in on the original XY plot, or I can zoom in here on the time and X plot. Now note that this is going to be a little bit confusing because Desmos automatically defaults to X and Y. And moreover, this has X2 and Y2, whereas the other one was X sub 1 and Y sub 1. So they are different variables as far as Desmos is concerned. Okay, but we need to talk in terms of, I know this first column is T, but it's not going to be T for now. It's going to be X2, and this is going to be Y2, and I know this Y2 is actually our X values from the graph. So our goal now is to fit a curve to this set of points. Okay, and we can play with different types of curves. I find polynomial curves are really very good for fitting irregular shapes. This is not a repeating pattern like a sine. It's not a ski jump like an exponential function. But polynomial functions are probably the best way to go. Now remember it's x2 and y2 that we're fitting this to. So here's how you do what we call a regression, a curve fit in Desmos. You type y2, because remember that's the y value that we are using, and we type tilde. Tilde is on the top left of your keyboard next to the number 1 key. It's a shift tilde. Okay, and we read this as y2 takes the value of. Y2 takes the value of. And now we are allowed to put in what we call coefficients, or constants. And to keep them straight, I find using subscripts helps. I can do coefficients A, B, C, D, etc. And you run into some trouble because some of those letters are reserved, like E. E is a constant whose value is 2.714, right? So you get into trouble a little bit that way. So I'm going to use subscripts. I'm going to say A1. Now that's a linear function right now, but it's a horizontal line, plus A2, another coefficient, X1. And it's important to put in that X1. Oh, X2, sorry, X2. Now you'll notice you can see a line that seems to fit, kind of, right? And that's because I've got a first-order polynomial equation, or a polynomial function. I've got a constant plus a constant times a variable, right? Let's go on. I'm going to increase the order by saying my third coefficient, x2 to the third power. Okay, and now we've got a quadratic, right? Not to the third power, to the second power. There we go. Now we've got a quadratic that's fit, right? And it works really well if you start from simple and go to more and more complex until you get a good fit. Okay, so let's do A4, our fourth coefficient, still variable x2 to the third. Now we've got a cubic function. Now we got a pretty good fit. I might explore going up to the fourth power and the fifth power a little bit here to see if there's much improvement. But that's a pretty good fit. Let's go A5, x2 to the x2 to the fourth. Okay, and that's actually a better fit. I like this better. Now I think we're going to get diminishing returns. So if I do A6, x2 to the fifth, we really don't see much better fit. And the degree of the fit can be read by this r squared. We call this the variance. The r squared value, 0.9983. The closer that is to 1, the better the fit, right? 1 would be a perfect fit, that the function goes exactly through. So if I back it off to the fourth order, 0.9983, there's no change. Okay, so I'm going to stop right here. We've got a fourth order polynomial equation that fits our x values, given our time values, our t values. And you can note the coefficient values down here. The A1 is negative 75.0386, etc., all the way through A4. We're going to need those later on, so keep track of those. All right? So we've created a formula that fits the x values given time. Now I need to create a formula that fits the y values given time. All right? Now, unfortunately, to copy and paste from Excel to Desmos, it has to be a contiguous block. I can't, copy x or t and y. You can select in Excel that way by holding down Control and whoops, I held down Shift instead of Control. Holding down Control and doing that, but unfortunately you can't paste like that. It's going to try to insert all three columns. So Control C and Control V, right? And now this is T and Y. Okay, and I'm just making a new block out of this so that I can copy and paste a contiguous block. So my T and Y values, I'm going to copy, Control C, and paste, Control V. Okay, now notice the variables are now x3 and y3. x3 still represents time, y3 represents y, and it automatically zoomed in to our graph. If it doesn't, click the plus magnifying glass on the bottom left. Okay, so now I need to create a polynomial function that fits this. So again, I'm going to click in the next cell, and I'm going to say y3 tilde. Now we used a's for our coefficients on the x function. So for the y function, I'm going to use b's, just to be systematic. So b1 plus b2 x3. Okay, so there's our linear function. That's its fit. Plus b3 x3 squared. There's our quadratic fit. Not too bad, but not too good either. Okay, b4 x3 cubed. Okay, cubic function, a little better fit, plus b5 x3 to the fourth. Okay, that's pretty good. I might go to the, notice our R value, 0.992. That's a pretty good fit. Let's try one more, b6 x3 to the fifth. And that's not really much better. And I think, I could, there's kind of a diminishing returns. So I'm going to stop at a fourth order polynomial function again. Okay. All right. So there we go. We've got our polynomial function for our x. We've got our y. We've got our polynomial function for our x. Okay, now the trick is to enter the parametric equation for our original storm and see how it fits. So we're going to try to get a graph that fits this. Okay, so we're going to scroll down here, and here's how we enter our parametric equation. In Desmos, you can type a parentheses and put a point, so like 2, 3, right? And it'll graph that point. But instead of coordinates, I'm going to put a formula based on t. Okay, t is our parameter. All right, and the cool thing about it is, since I was very systematic in my use of coefficients and stuff, I can remember the formulas. So we're going to enter a1 plus a2t. Notice I'm not using x anymore, I'm using t, plus a3t squared plus a4t t cubed plus a5t to the fourth. And that was our fourth order function for our x values. Comma, and now I'm going to put in my my formula for y. So b1 plus b2t plus, and notice there we're starting to get something here, right? Because it's calculating. Plus b3t squared plus b4t cubed plus b5t to the fourth. Close parentheses, right? Okay. All right, now notice that it's only got a little bit of a glitch, and that's because it wants to know what about t. It wants to know a t range. Right now it's only going from 0 to 1, so I'm only plotting between 0 and 1. There were 16 points, so I'm going to plot, I am on camera by the way, 16, and there we go, right? And that was my wife ringing my key. All right, and so this, you notice, is a pretty good fit. And really what we want to do here is, if we're going to predict where the storm might go later, we might extend that to, say, 20, right? And now we've got a projected path for the storm to follow. Now, I will say this, extrapolation is always really tricky, and weather is not a simple system. And so extrapolation is even with the best computer models developed on supercomputers, only accurate for a little bit. The further you get outside the bound of the data points that you use to create your model, the more error is going to be introduced. And that error is multiplicative, it's exponential, right? And so we can use this to predict, but we can only say, take it with a grain of salt. All right. So one last thing that we need to do, is we need to record our formulas, our parametric equations. And so let me get down to, got so many layers. Get down to here. So here's our formula that I calculated here. And I'm going to go back. Here just to show you what I'm doing in Desmos. I'm going to go back here to my A's, right? My A coefficients, right? And we're going to enter, and you don't need to include all the precision that they have here, but here's my parametric equation. Okay, so we have A1. Actually, let's get there here. A1, negative 75.04. Negative 75.04 plus A3, A2, negative, so minus 1.15. Okay. 15, yeah. 159. Go 4 sig figs on each one. Okay. Plus 0.08867. Oh, forgot t. And t squared. Okay. Minus 0.02034 t cubed. Plus 0.001052 t to the fourth, comma, and I'm not going to have room to do this here, so I'm going to add this down below. Now I'm going to do my b's, my y function. Okay, so 22.64 plus 2.523 or 524 t p3 minus 0.6205 t squared. All right, and plus 0.05191 t cubed. Okay, minus 0.001194 t to the fourth. I find it interesting that the magnitude of the coefficients starts out fairly large and gets smaller as you go to the higher degrees, the higher powers. That's interesting. All right. Okay, so that is the goal here of this. So let's consult the worksheet again to make sure of what we want you to do. So find your hurricane, plot the hurricane path. This table, if you do it in Excel and Desmos, like I said, does not need to be filled out. You do need to write your final equations, right? And so you can use Desmos to type the equations, but you need to start with a quotation mark to make it text. All right, and then check your model. Now, the way you check your model, we don't need to do this table here. We need to check our model by turning in a screenshot of this, right? In fact, I'm debating whether or not we want screenshots of all of them. We want screenshots of your curves. Let's not. Those are necessary all along to get the final product. So I will assume you've done it. And give me this graph, right? This graph with that gives your x and y values for the storm and the graph of the parametric equation to show how it fits. Okay, and it needs to fit fairly accurately here. Okay, now there's a little bit more on the table on the graph. So answer these questions. You can answer these in Excel, or the way to answer them in Desmos, if you want to turn in a Desmos file, and actually that's an option too. If you want to turn in a Desmos file, you can plus and put in a note, and you can answer the questions there. That's a possibility too. Or you can answer them in Excel, or you can write out your answers in a Word file. Okay, So there's a few things. A screenshot of this is necessary, as well as your answers to these questions. How does your model compare? Why did you choose the graph family? Is it possible to solve for X for T, substitute into Y and eliminate? Okay. By the way, the answer to that question in this case is no, because this is not a function. It fails the vertical line test. And so we cannot write a function of x of y depending on x, okay, because it fails the vertical line test. All right. Let me know if you have any questions. Feel free to book a live lesson.